Alright, time for a little fun. I've purchased this Ultimate Crystal Radio Cat's Whisker Diode Kit, the Craftsman version from United Nuclear Scientific Equipment and Supplies. Okay, what's in this? A piece of sandpaper, 220 grit, the instructions. Thank goodness they provided printed instructions. So many kits these days don't. And let's see, they're germanium crystal, associated hardware, terminals, washers, screws, some little, looks like little plastic wafers, a metal adhesive disc, I guess, a couple of wooden pillow blocks, and some 3M like bump-ons for the feet. The wood looks like a decent quality hardwood, already machined. Still needs to have surface treatment like varnish, stain, whatever. 2 little vials of wood stain and polyurethane, so you don't have to buy your own. Roll of wire with some sort of varnish on it for insulation. A knob, a crystal or piezoelectric earphone, some crimp terminals, and a little bit of wire and a variable capacitor. Oh, and the piece of, I guess it's PVC, black tubing, which will be the thing that the magnet wire gets wound around for the coil. Let's take a look at the manual inside real quickly. Oh, by the way, United Nuclear Scientific is in Klamath Falls, Oregon. So there's a history and operations section, identification of all the parts. If you have the easy assembly version, skip this page. There's some preparation to be done. Cutting the wire up, putting the lugs on it, soldering the wire to the variable capacitor, and winding the coil, varnishing the coil, putting double-sided foam or double-sided adhesive foam on the variable capacitor, mounting it in the base, wiring things up, assembling the cat's whisker, and then how it should be when it's finished. Then instructions for setup and testing. Making the antenna, radio testing, cat's whisker tuning. I also forgot to mention that it comes with a little brush, presumably for stain and varnish and things like that. I'll find out. There's also in here, which I didn't note before, there's a resistor and a diode. I believe that's a germanium diode. My understanding is if you don't want to use it with the actual cat's whisker detector, you can substitute the germanium diode and get it working that way. Alright, all those bits are separated from the bag. The resistor and the diode are there. Terminals, screws, magnet wire, feet, pillow blocks, hookup wire, ring lugs, variable capacitor, earphone, stain and varnish, cat's whisker components, and the coil form. And the sandpaper and the base are over there. First up is the preparation of 2 Jumper wires, 2 inches long, plus the crimped and soldered ring lugs at the end. They are set up to be crimped with a crimper. Most people probably don't have a crimper. And even when I use the crimper, the lugs, probably to fit the large screw sizes, have an overly large, correspondingly over large crimp area for the gauge of the wires, so even when you crimp it, the wires can still be loose in there, which is why they recommend soldering it as well, which I did. The variable capacitor has 2 terminals. There's 2 different lengths of lugged wire coming off of one of them, and a longer length of lugged wire coming off the other one. There's the magnet wire wound around the coil. There's probably enough extra wire to do a couple more wraps, but the instructions just say wire from the holes that are drilled. And even though I was trying to wire this very tightly, it ended up where I probably could have got at least one more wrap on there. It's not that critical, but now is not the time to try to fix that. Alright, there's the varnished coil. Slathered it on liberally and brushed it around a few times. Make sure it's down between the strands of wire as much as possible, or the wraps of wire. And also making sure it goes over onto the form to help cement the lacquered coil into place on the form so it's not sliding around. Alright, here's the wooden base. That's the top side. There's the bottom side with the United Nuclear Scientific logo laser burned on there, it looks like. That's clearly the bottom, and also because it has the recess for the tuning capacitor. And there's also these 2 little pillow blocks which are for mounting the coil. And they give you the piece of sandpaper and a little vial of wood stain, which the instructions don't mention varnishing after using the stain, so it may be a combination stain and varnish. Anyway, they just recommend doing the light sanding. It's already pretty smooth, just to get any little burrs and things off of it. And then applying the stain with a rag and wiping it in, waiting 10 minutes, wiping off the excess and letting it dry. Alright, this is the stain color I got out of it. I've let it go 10 minutes and then wiped it down firmly with my rag, and that's the color I got. It's a pleasing color. Okay, it's time to mount the tuning coil at this point. So I'll put these 2 coil supports aside for the moment, and we'll flip this thing over like this, and it should just fit in there. It doesn't have a mounting knurl or anything, so it does have a couple of threaded screws or threaded inserts from which you can put screws in to mount it. And I might have to do that, but they recommend just using the included double-sided foam tape. The double-sided foam tape that was supposed to come with this kit did not. I triple checked all the packing materials and everything, and it just doesn't seem to be there. Luckily I stocked some of the product and cut out 3/4 inch by 1/4 inch strips and have adhered them to the front of the tuning coil. And now they have to be flipped over and go into there. So that goes in like that. And that side is there. It's a little tricky to get it in there so it doesn't rub in the hole. And I think the one I have rubs a little bit, but it still turns reasonably freely, and I think that'll be fine. The 3 wires coming off the variable capacitor and the additional jumper wires have been screwed onto the base using the included brass screws, washers, and thumb screws. There's a bit of a manufacturing problem on these two. They have longer screws, and the screws are supposed to thread into the holes in the wood, so you know it's not really tight, but it's enough that it grips them in place. You really have to drive them in fairly forcefully with a screwdriver, but the holes for these two were oversized, so the screw would pretty much just fall right through the hole. Not with any wiggle room, but you didn't have to really screw it in, you could just push it in. Therefore, when you loosen the thumb screws, the bolt wobbles around, and it's not supposed to be that way. Even with the screw loose, the thumb screw loose, it's supposed to pull tightly on the head against the jumper wire. So I haven't come up with a good solution for that yet. I thought about trying to stick a little super glue into the hole in the wood, but that's not really ideal. So for the moment I'm just leaving it the way it is, and if I come up with a solution later I'll apply it. And then the 4 rubber feet stick on to the bottom. The brass or gold colored decorative decal has been put around the shaft of the tuning coil. The wire on the coil is trimmed to about 2 inches extending out, although I did arrange to tuck another 1.5 inches or so back inside the tube just for good measure, and then scrape most of the insulation off, or scraped all the insulation off about the last 1.5 inches of the extended wire, using sandpaper that was included for sanding the wood, and then scraping a few spots that didn't seem to want to come off easily with the sandpaper, just using my X-Acto knife blade. Well, I think I found the double-sided foam tape. It's like a transparent product. It's not foam, but I think it is the adhesive tape that's supposed to be used on this. So I'm going to switch over to use that. I did read ahead through the manual, or the assembly instructions, and didn't say any place where this would be used other than as a substitute for the foam tape. So some of the double-sided plastic is used to affix the coil supports to the non-wrapped part of the coil form. This stuff is awfully squishy, and it's not long enough to run the full run of this, so I decided that I was going to go back to my own stock of double-sided foam and just cut out necessary pieces. Okay, the coil is now affixed to the base. And I'm supposed to make loops at the ends and put them around these at each end. Alright, the coil wires have been wrapped around their respective binding posts. I had it set up so the back of the coil is pretty much in line with the rear of the wood block. Alright, I'm soldering up the cat's whisker holder. There's this piece here, and then there's a little like a square with 3 corners lobbed off that gets held more or less centered there, and then has to be soldered in place like that. It only needs to be at that one point, not the rest of the way around. Alright, I'm putting the soldered assembly onto this one post at the front right corner. I hadn't noticed until now that this has been treated. It seems to be more than just sanded, because I think these are just brass pieces. But how come it has a silver look to it? It may be, I don't know. Anyway, this is correct according to the assembly photos and the assembly instructions. There we go. Now here's the actual cat's whisker. It looks like this is made out of a safety pin that's just been kind of taken apart and bent up. I'm not sure. It definitely has a sharpened point here, and then this side's bent to go around one of the lugs. There's the cat's whisker installed. It's supposed to be bent to aim pretty much at the center of the little shallow basin here, but not actually touch it. It should be kind of hanging in space above it. So when the crystal's put in there, it'll center in the basin, but the spring force will push down slightly on it. And here's the crystal earphone. Its wires are connected to these two terminals. There's also a 47K resistor, like an 1/8 watt or maybe even a 1/16 watt across there. Its leads are bent out a little bit just to help handling it, because otherwise if you don't have something to grab onto and you're turning these down, it wants to just slide out from under them. So those are there to kind of hang on to prevent that from happening. Alright, the knob has been put on the shaft of the variable capacitor. The kit includes a germanium diode. It's recommended that instead of doing the initial test of the radio with the cat's whisker, that the included germanium diode be used in its place. So that's just connected across the two terminals that would normally have the cat's whisker touching the crystal down there. So what I'm missing here is an antenna. They recommended a 100-foot antenna. I'm thinking of, I also need to get a good ground, and I don't have a good ground here, and you can't just wrap it around a water pipe. There's no water pipes anywhere near where I'm using this radio. So the best way to do it is probably to just use the ground of the house's electrical system. And that's a common thing. They don't mention the instructions of this particular kit, but I know that that's a common method used for primitive radios like this, that you just make up an AC plug and use only the ground lug and connect a wire from that and let that be your ground for the radio. I don't happen to have a handy spare plug at the moment, so I'm going to run to the hardware store tomorrow and get one of those. And they also recommend getting a couple of short stubs of PVC pipe or pipe nipples and using those as insulators for the ends of the antenna itself, where it may be strung from tree to tree or whatever, so that you definitely have the antenna isolated from whatever it's tied to at the ends. But otherwise the radio is complete in its assembly at this point. Alright, I just have a inexpensive 3-prong plug from the hardware store and some stranded, I think it's 22 gauge wire with green insulation I'm going to use as the ground. This only needs to be connected to the ground pin. Well, I have, I don't know, I think it's got to be close to 100 feet of, I don't know what gauge it is. It's much thicker than is necessary. MTW 14 gauge, yeah, it's just, but it's stranded. I bought this by accident when I was trying to get solid wire and just kept it around for who knows what. I've also just got some basic steel wire that I always have in stock, and a couple of whatever size these are, PVC nipples from the plumbing section of the hardware store. I'm going to make sure I have the antenna fully insulated by using these. Really, the insulation on the wire itself should be adequate. I should just be able to wrap this around a tree or whatever and call it a day. But I thought it would be easier to wrap the steel wire around something, since it'll twist and hold better, and then use these to insulate between that and the actual antenna. Alright, here are the insulator tubes, crudely drilled out. Alright, I'm just using my fence instead of a tree because it'll get me a longer distance uninterrupted. And then I just have the insulated wire through the insulator, and since it's stranded and fairly stiff, it'll probably unravel, but I wrapped a little tape around it. And here's the other end. I just wrapped it around the grill of my air conditioner condenser because it was in about the right place. And I wrapped the wire back around and then stripped off the end quite a bit so I can easily twist on the lead that'll run into the house. And it's hardly dragging on the ground, but that's about as tight as I could pull it. I've twisted the antenna and the lead running into the house together just like that. Okay, I have my ground running down here and connecting to this side of the coil, and I have the antenna going to this side of the coil, and the earphones connected down here as already shown. Now, if everything's working, I should be able to tune in something on the headphones or the earphone. I'm going to try to put the earphone up next to the camera's microphone.
You'll love Rasny Jewelers' incredible value. Don't make a mistake and end up with a poorly cut diamond. Rasny diamonds are top quality cut and sparkle. There's a salesperson there that will help you, and it'll be a very personal, educational, fun experience. At Rasny Jewelers, it's the start of a relationship. Their team will share their experience so you're confident in your choice. Chicagoland's local jeweler, Addison Hensdale.
So the intelligibility of the AM signal is very clear, and it's not too hard to hear through the earphone as long as there's not other noises around. Sitting here in my basement with the air conditioner blower going, but I can definitely listen to the station easily. And then that fades out. There's another station there. They're talking about Medicare, signing up for Medicare there. There's somebody talking about they don't have the man hours for something or another. Not really hearing anything else on the rest of this, but definitely around here there's 2 or 3 stations. That's probably the best I'm getting. I'm not actually going to try to make a video of messing around with the actual cat's whisker on here. I'm considering that mostly just for display purposes. They're notoriously hard to get working well, and since this is just the bent piece of wire, I think I could be futzing around with this for a long time. And you know, I'm just proving that the radio works using a germanium diode here instead of the cat's whisker diode. That's all I really need to do. It's really just for display, but I hate to display something that doesn't work. And this is definitely working, and working as well as I would expect any crystal radio to work. So, good job. Alright, I'm going to talk a little bit about the theory of the crystal radio, in case anybody doesn't really understand how they work. I'm going to start out with the fact that the crystal radios work with AM radio signals, in other words, amplitude modulated radio signals. So what does that mean? So here is a sine wave, very poorly drawn sine wave, but let's say you have a radio circuit oscillating at a particular radio frequency, much higher than the frequencies used for audible sound, in other words, in the radio frequency band, and you want to impress on it speech, music, whatever. So you have to modulate it one way or another. The two most common kinds are amplitude modulation, or AM, and frequency modulation, or FM. FM is too complicated to really do with a crystal radio, although I've heard some people have had some clever ways of kind of doing it. But let's stick with the amplitude modulation. So what we have is these higher frequency, signal in the circuit, and then we've got, I'm just going to draw it as a sine wave, but in reality it'll be more complicated. So let's say that we have, this is the sound, so we modulate this with the amplitude of this. So if I just superimpose on there, let's say this is ground here, so this is going to be our base level here. So we're going to have, well, I'm going to put the base level on here anyway, but so we start out with, a lower amplitude sine wave, and then we go to a higher amplitude sine wave, and a higher one, and a lower one, and etc. So the height of each part of the radio signal is amplitude modulated to fit the shape of the audio signal. This is a really crappy sketch. I wish I would have done it better, but I think you get the idea. So you end up with, instead of this signal, you end up with, again, this is the baseline, and it's alternating above and below that. So you might have a signal like this, and then it might get bigger and bigger, and then the amplitude of the audio signal gets less and less, so it gets smaller, and this would reflect a audio signal amplitude that's going up and back down. It kind of fits this shape. So that would be amplitude modulation. Now let's just assume that we have radio signals out there that have amplitude modulated stuff going on, and the amplitude of the audio signal is something you'd want to listen to with your radio. So we need to demodulate this. We need to take a signal that looks like this and turn it back into a signal that looks more like a proper audio signal at an audio frequency. You've got to strip out the higher frequency part. Well, I think I'm actually getting ahead of myself here. I should have started with, how is a radio signal received in the first place. So let's put the demodulation aspect of this aside for a moment. And we know we've got this amplitude modulated signal going out in the air. It's an electrostatic signal, so it is not related directly to magnetism. It's an electrostatic signal, and it can be retrieved from the air by giving it a path to ground, and that would turn it into a voltage. So the easiest way to do that is to get an antenna. This is a schematic symbol for an antenna. And you run a wire through some kind of resistance that's not even really critical, but you run it down there and you get it back to earth ground. because these signals are out there in the atmosphere, and their voltage, if you will, or the amplitude of the electrostatic charge is relative to earth ground. So when we run a wire from the air, the aerial, if you will, which we like to call an antenna, and you give it a path to ground, you're going to end up with a voltage flowing through this wire that is the same pattern as the electrostatic radio signal that's out in the air. So that's how we convert the electrostatic signal in the air into a voltage in a circuit. Well, now how do we tune out other stations? Because we know that there are different stations out there in the air, and they have different frequencies. That's how you tune them. Well, you have to find a way to reject frequencies that are above and below the one you're looking for. In other words, radio frequencies that are too high should be rejected. Radio frequencies that are too low should be rejected. Only the radio frequencies pertinent to the station you're trying to listen to should be passed into the rest of the circuit. So we modify this, we replace this resistance, whatever that would be, with a tune circuit. So we take our antenna again, and the most common way of doing this, the simplest way of doing it, is going through a coil and then to earth ground. And that's not enough. We know that current through an inductor, which is what the coil is, to the voltage here and the current, it's going to choke higher frequencies. So as the frequency of the signal goes up, this is going to look like an increasingly greater resistance, and it's not going to allow so much of the current for that frequency to go through it. So that would be a way to change the selectivity of this circuit by not responding to frequencies that are inappropriate in one direction. And then we can go over here and we can take a capacitor and put it across the coil. And the capacitor has the opposite effect of the inductor. So when the frequency of the electrical signal gets higher, this starts looking more like a short circuit, and it passes that through it, whereas this is rejecting the higher frequencies. But if you have a lower frequency, that'll go this way, but it'll look like this is an open circuit to a lower frequency signal. So these two in parallel, if you pick their values correctly, you can set it up so, let's say you've got a signal that's, well, it's going to be too hard to draw that. If I had an oscilloscope pattern, I could probably do it easier, but just suffice it to say that you're going to be looking at the signal being blotted out or not responded to, just keeping it simple. But as we get close to the radio frequency we're interested in listening to, all of a sudden the response of the circuit goes way up and we start getting good signal. But then as we get higher in frequency, it goes way back down again. This, by the way, is increasing frequency in that direction. So we end up with this narrow band on either side of the desired frequency, and anything much lower than that is just muted, not responded to, whatever you want to call it. Anything much higher is also muted or not responded to. So we can adjust these values to get a similar effect. Now in reality, this is going to be a low quality filter here, and radios that have better qualities in this regard have more than just a simple capacitor and inductor. But for a crystal radio, it's good enough. So let's go back and make a cleaner version of this. So I'm going to have my coil again, going to ground, and I've got my capacitor around it, and I want to make it adjustable. Well, the simplest crystal sets used an adjustable inductor, and they did that by wrapping wire around a coil form and then scraping the insulation off the wires along one edge and then dragging a contact along it, so you were effectively having just a little bit of the coil or more of the coil or more of the coil, thereby changing its inductance and therefore its response to certain frequencies. Now that's a kludgy way to do it, and people had problems doing it that way, but that was probably the simplest, serial box technology approach. These days we're more likely to make the capacitor adjustable, so instead of a fixed capacitor we use an adjustable capacitor. So you turn a screw or a knob and it changes its capacitance and thereby changes the frequency that this responds best to. Now you'll probably see some crystal radio circuits that don't have a capacitor here at all. All they seem to have is the coil. There still needs to be a capacitor here for it to have any selectivity, unless you just only had one radio frequency that was out there within range of your receiver, and so you didn't have to really tune it. You could dispense with that, but in fact, unless you have a really long antenna, for reasonable lengths of antenna somebody would have with a crystal set, the length of the antenna is still pretty short compared to the wavelength, and it doesn't respond very well in that regard, but it still responds well enough. But a characteristic of antennas that are the wrong length for the radio signal wavelength that we're talking about, they have a certain capacitance. They act like a capacitor from here to here. So even if you didn't have a physical capacitor here, the fact that there is essentially a virtual capacitor here by virtue of the antenna lets you get away without having the capacitor. But we want the capacitor here because that's how we're going to tune this resonant circuit. Now we can get back to the old demodulation thing. How are we removing the radio signal and leaving only the audio signal? Well, let's look at the radio signal again. Here's a ground potential, or a 0-volt potential anyway, just a reference line. And we've got these signals here. They're always the same frequency because AM uses a constant radio frequency, but the amplitude varies. So I'm doing a bad job of drawing it, but you've got a signal whose amplitude is going up and down, but it's always the same distance from here to here, here to here, here to here, and so on, because it's a constant radio frequency. Well, this is AC. We could say that this is 0 volts here. And if you were to connect, say, some headphones or try to listen to the signal, you'd hear essentially nothing, because what you're really going to hear is the average of the voltage. You can't hear the radio frequency signal, but you'll hear the average of the voltage, if you hear anything at all. And that would be due to the response of whatever you're using to convert this into audible sound, a speaker or whatever. So you can't have this signal going above and below ground. The easiest way to get rid of that is to put a diode in it. So let's come over here. We've got a voltage developed across this, and so now we're going to come over here and put in a diode, which only conducts in one direction. Doesn't even matter which way the diode faces, because we're not really concerned if we're trying to look at only the part of this that's above 0 volts or the part that's below 0 volts. For this, it doesn't matter. And we come down here and then we have, you know, our headphones, earphones, whatever. And then back to here. So we're trying to cut out half of this so it's no longer alternating above and below 0. The dial will do that. If we have it set up this way, it will only respond to the positive voltages. Therefore, everything below that 0 volt line is going to be cut off. And we'll end up with, here's the 0 volt line again, we'll end up with you'll end up with this. And so on. Now that's a pulsed high frequency signal. It's still the radio frequency signal, but it's in pulses, and if you use something like a headphone to interpret that signal as an audio signal, you know, sound waves in the air, in other words, it's going to do this because it can't respond at the radio frequency. So what it's going to do is it's going to average this out, and the average of this signal, remember everything's above ground, so there's no negative portion to average out and cancel the upper part. It's all going to be stuff we can use because it's remaining above this. You're going to get an average signal that, you know, looks like this, right? And that's going to be your audio signal. And so ultimately you're just going to have, you know, whatever the audio signal shape was, you're going to end up with this. And that'll be the voltage, or at least the averaged voltage that's presented across the earphones. So that's how we convert the amplitude modulated signal into an audio signal that we can listen to. Well, let's look at that detector again. And we have a couple of terminals here, and we connect up a twisted pair of wires, you know, several feet long probably, and that's going out to our piezoelectric headphones. And then we end up with, at the end of this twisted wire cable, we end up with, I'm going to use the schematic symbol here for a crystal. That's the symbol for a piezoelectric element. It's also the symbol that's often used for a crystal, like you'd use in a crystal oscillator, but it's the generic symbol for a piezoelectric or a crystal of pretty much any type. You'll more often see a modified version of that, which looks like the schematic symbol for a speaker, and then you sort of superimpose the two sides of the crystal, and that suggests a piezoelectric speaker. But a lot of times we just make the simple schematic symbol for a it's kind of like this. You don't want to draw this. I kind of did it before, but this is actually the symbol for a circuit breaker if the line doesn't actually touch these circles here. But if you do it more like this, and if you use a bigger circle for these, there's a lot of variations on this, but you try to make it kind of look like a pair of headphones and do that. So instead of doing this, ta-da, we have our representation of our piezoelectric earphone here at the end of this twisted wire. Well, a piezoelectric element by itself has some capacitance, and twisted wires have some capacitance, as untwisted wires do, but the close proximity of the two wires makes it more capacitive. and they stay in close proximity because they're twisted together in this cable going there. So we have this capacitance that's inherent to the earphone or the earpiece with the capacitance of the wire, and this looks like a capacitor here. So not only are you looking at its resistance, but it has like a capacitor in parallel with it. That capacitor, it's a fairly small capacitance value, and therefore it's particularly good at shunting or shorting out, if you will, the higher frequency aspect of this and responding only to the lower frequency part. So the simple fact that we're using this cable and this piezoelectric or crystal earphone here helps electrically with filtering out the high frequency aspect of the detected signal and leaving only the lower frequency part that is what we actually want to listen to. So that's sort of a hidden feature, sort of like the capacitance of the antenna being a surrogate for having a capacitor in the circuit, albeit an untunable one. So we've now got to the point where we've demodulated the signal. We've received the signal and turned it into an electrical signal from an electrostatic field change, and we've detected the audio frequency out of it, and we've filtered it partially just by our own hearing, partially by the physical characteristics of the piezoelectric earphone, and partially due to the capacitance of it. So all those things acting together leave us with just the part we want. And if there was a little higher frequency part left over, it's a little low volume and you wouldn't be able to hear it anyway. There's another refinement to this. It turns out that we have to think about impedances as well. In this general radio circuit for the crystal set, the impedance of the antenna is got one thing, the impedance of the capacitor and the inductor here is another thing, the impedance of the headphones and the headphone cord is another thing, and they're not all the same. Because the crystal set gets all of its operating power from the electrostatic field in the air, and there's no other power source, it's always going to be a weak signal that we're listening to with our ears. But in electronics, or even just in electricity, there's a whole theoretical aspect to the behavior of signals when you're transmitting them from places to places, and a small part of that has to do with power transfer. When you want to get the most power transferred from one place to another in a circuit, and you've got different impedances, it's best if all the impedances are the same. But we know we've got different impedances here. It turns out that the impedance of the piezo headphones is too high compared to the upstream radio circuit to get optimal power transfer from that circuit into the earphones. So we need to do something to lower the impedance of this. And since the impedance you can look at as being a resistance, and a way you make a resistance into a lower resistance is by putting another resistance in parallel with it. So we'll take this resistance or impedance that's here, and we'll put a fixed resistor across it. And we figure out what this is. You could do it theoretically, or you could do it empirically by just doing tests in your laboratory to figure out what resistance of resistor here gives you the loudest signal here, and then pick that value. A common value if you're using a piezoelectric earphone is something in the order of 50K. 47K is a very common value, so you see that value used a lot. 47K. Okay, so let's look at the actual crystal radio that is embodied by this particular kit. So we end up with our block of wood, and it has a coil on it. With the wire wound around it, and that's terminated to a screw that's in the wood, and the wood is a good insulator, so we have our coil between these two screws. And we connect an earth wire that's going off of the radio, and it's going to something that gets it a good connection to earth ground. And then we have a wire running off of this screw, and it goes up and it connects to our antenna that's, tied between two trees, or between two fences, across fence posts, or whatever you've got. Back in the day, people used to use the coil spring and frame of a bed, or the metal fire escape of their building. A lot of things, but it needs to be the antenna, and then you tie onto it with a lead that runs down to the radio. So you've got that connection. There is a tuning capacitor on here. And it's underneath the wood, but it has wires on it. And one of the wires is connected on the bottom up to this screw, and another wire is connected on the bottom to this screw. So you can see that you've got the capacitor wired across the coil, and the antenna on one side of that, and the ground on the other. So that is this much of the circuit right here. Then we have two screws here and here, and these are connected together with a jumper on the back side. And between these two terminals we have a diode. So I'll just draw a diode in there. This diode can be a germanium diode, it can be a cat's whisker diode using a germanium crystal or one of the other types of mineral that can function in this way. Germanium is probably the most popular, at least these days, but something that acts as a diode. And then we have two more screws, and there's a wire that comes from here down to here, and this also has a jumper wire going to here, and this has a jumper wire going from here to here. And between these two terminals is a resistor, 47K. You can actually put it on the top or on the bottom, but it needs to be there for best results. And then finally, we come over here with our twisted pair wire, and going to our piezoelectric headphones. So that is the entire radio assembly, and how you can relate it to the schematic here.